This unit focuses on introduction of hydrocarbons. By the end of this discussion, you will have a good understanding of what we mean when we use the term hydrocarbon. You'll understand the different types and classifications of hydrocarbons, and you'll know some fundamental features of these types of molecules. First off, we need to get the definition out of the way of what we're referring to when we say the term hydrocarbon. Hydrocarbon, by definition, is going to be a molecule that has just carbons and hydrogen atoms in the molecule. So no heteroatoms. Remember that heteroatoms are non-carbon, non-hydrogens. So hydrocarbon, hydro is what refers to the hydrogen in this. Carbon, of course, refers to carbon. So it's going to be a molecule with no heteroatoms. So a molecule without heteroatoms. Heteroatoms, remember, anything except carbon and hydrogen. And the other way to define this equivalently is going to be it's a molecule with just carbon and hydrogen atoms. We can split hydrocarbons into a total of 4 different groups or categories. We're going to look at those groups and categories now and come up with some terminology and definitions and some helpful hints for dealing with those types of hydrocarbons. So I'm going to go ahead and split my hydrocarbons into a total of 4 different categories. So everything under this umbrella of hydrocarbons. We're going to start with alkanes, which you should recognize alkanes from the discussion of functional groups from earlier. Alkanes are molecules that have just carbon-hydrogen bonds and carbon-carbon single bonds. So only carbon-carbon single bonds can be present in a molecule that's classified as an alkane. And a fun fact about this is that if the alkane is an acyclic alkane, meaning there's no ring structures in the molecule, then you can come up with the molecular formula for an alkane as long as you know the number of carbon atoms in it. So the molecular formula for an acyclic alkane will follow the template of Cn, where N is the number of carbons, H, 2N plus 2. So this is a really useful formula if you've drawn out the structure of an alkane that perhaps has several atoms in it, and you don't really want to go in and count up manually all of the hydrogen atoms that are in it. As long as you can go through and quickly count up the number of carbons, you can use this formula to calculate how many hydrogens that there and take definitely a lot of time savings in doing that. Alkanes are referred to as saturated hydrocarbons. Saturated hydrocarbons, or saturated molecules in general, refer to molecules that have no carbon-carbon double bonds. They have just carbon-carbon single bonds, and the term saturated is also similar to the term used to describe saturated fats, where saturated fats are fats where the molecules, the carbon chains, have just carbon-carbon single bonds and no carbon-carbon double bonds. When we say the term saturated, what we mean really is that the molecule is saturated with hydrogens. So I'm going to put in parentheses here, saturated parentheses with hydrogens, meaning that we've maxed out the number of hydrogens per carbon that the molecule can possibly have. If we start installing carbon-carbon double bonds or carbon-carbon triple bonds, we have to remove hydrogens as a result of putting in those double bonds or triple bonds so that we avoid going over the octet rule. So alkanes are what we refer to as our saturated hydrocarbons, and that terminology super analogous to the term saturated fat. Going onward, a second type of hydrocarbon is the alkene. Alkene molecules are ones that have one or more carbon-carbon double bonds, so it has that pi bond going on. And for an acyclic alkene, if there's one carbon-carbon double bond, the formula of the molecule is going to follow the template Cn, H2N. So you'll notice here in going from the saturated alkane, ane suffix, to the alkene, what we've had to do is we've had to remove a couple of hydrogens from the molecular formula, because we went from the formula being 2N plus 2 to just being 2N. And so therefore, alkenes are no longer saturated with hydrogens. Instead, we refer to them as unsaturated molecules. And this terminology also applies to unsaturated fats. Unsaturated fats are molecules where at least one pair of the carbons in the chain are connected together by a double bond rather than by a single bond. Another example of an unsaturated type of hydrocarbon are going to be the alkynes. With that YNE suffix, alkyne implies that there's a carbon-carbon triple bond within the molecule. And if there's just one carbon-carbon triple bond in the molecule and the molecule is acyclic, meaning no rings, that means that the molecular formula is going to be CnH2n minus 2. So if it's acyclic with one carbon-carbon triple bond, we're going to expect the molecular formula to be CnH2n minus 2. And so you'll notice here in going from the alkene, Ene, to the alkyne, Yne, that we've had to remove a couple of additional hydrogens so that we can avoid going over the octet rule when we install those extra pi bonds. Alkynes are also described as unsaturated molecules because they don't have the maximum number of hydrogens. And then finally, we're going to go ahead with the last category that we'll put hydrocarbons in, and that's going to be the category of our so-called arenes. Arenes are going to refer to hydrocarbons that have a six-membered ring with alternating single and double bonds. So this is going to be benzene, which is a six-membered ring, and molecules that are related to benzene that have perhaps carbon chains coming off them are classified as arenes. So the benzene structure that we've shown here can also be equivalently drawn as a six-membered ring with a circle inside. That circle illustrates that there's resonance going on amongst those three pi bonds to totally delocalize or spread those around the entire ring system. So arenes are going to be our fourth category of hydrocarbons. And arenes are certainly also classified as an unsaturated hydrocarbon because they have, in this case, multiple carbon-carbon double bonds. So with that, what we're going to do is take a look at an example where we can use these formulas to come up with information about the structure of a molecule. So let's ask the question here in this example. We're going to ask, what is the molecular formula of 4-isopropyl, 2,5-dimethyl heptane. So in order to address this question, what I'm going to do is draw out the line angle formula for this particular molecule. In the interest of time, line angle formulas are the best route to go. Then in that line angle formula, I'm going to count up how many carbon atoms there are and use one of the formulas up top here, the CnH2n plus 2 formula, since this is an alkane with that ane suffix, to determine what the molecular formula of this has to be. So I'm going to start by drawing my 7-carbon chain, heptane. So I have my 7-carbon chain. At carbon number 4 of that chain, I'm drawing my isopropyl group. At carbon number 2, my methyl group. And at carbon 5, my second methyl group. All right, so how many carbon atoms do we have in total in this molecule? And we can count those up or highlight those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is C12. And it would be pretty much a pain to go in and count up all the hydrogens here. It would take a lot of time. It's certainly doable, and you certainly should be able to do it, but we have a shortcut here because this is an acyclic alkane. And so C12 implies, if we use that CnH2n plus 2 rule, that if we have 12 carbons, our number of hydrogens here in this alkane have to be 2 times 12, which is 24, plus 2, which means 26. So we can immediately say the molecular formula of this molecule has to be C12H26. So these formulas are really handy for that. I definitely recommend committing them to memory because they will save you time along the road in doing problems like this and sorting out what the molecular formulas of molecules are.